And our next speaker is Professor Yang Gao, who is the Director of Space Technology for Autonomous and Robotic System Lab at University of Surrey. Today, she will be discussing AI robotics for sustainable space exploration and exploitation. So without further ado, now the stage is yours, Professor Gao.
A very good morning. From the UK side, I believe some of the colleagues might be in the afternoon or even perhaps evening time. So it's a pleasure to be here and invited to this conference. I give a talk and share some of my experience and latest findings through our research in relation to space robotics. I appreciate in audience, not everybody might be involved in depth in space robotics. Therefore, I thought to give a general overview of the topic. I think it's quite fair to say that the space robotics build on a multiple field of research. I mean, certainly we draw a lot of reference and learned a lot from terrestrial robotics, in terms of sensing, perception, mobility, locomotion, and navigation. We also benefit a lot from computer science research in terms of artificial intelligence, machine learning, soft computing, etc. Of course, it is also a topic that merge space engineering into the rest of the knowledge that looks at hardware, software harness, space qualification, system engineering in terms of putting things together and make them viable for space operations. The other areas such as biomimetics, advanced material IT, that we also draw a lot of relevance and information from. It is also worth mentioning the fact as space roboticists, we very often been driven by requirements and specifications in our design research from the scientific community for space. For example, the way we design Mars rovers, the way we design robotic manipulators in the International Space Station. Of course, more recently, there are other domains that working hand in hand with the robotics community, from the space law, architecture, and tourism. This provided a lot of additional dimensions to things we do. There's no doubt AI robotics already playing a significant role to enable existing space missions. I mentioned already about robotic manipulators that are being used on a daily basis in the space station. There are also robotic mechanisms to help deploy, things like the solar panel on geostationary satellite. There are Mars or lunar rovers. There are robotics being deployed in missions to comets, asteroids. This is a table that tries to summarize existing flown robots in space. And these are the quite successful missions. There are about 20 of them since the 1960s. Of course, the missions launched with robots, there are a lot more than this that have been, unfortunately, perhaps not so successful. So these are the lucky ones. But just to give you a flavor that how actually challenging it is to make things work in space, and particularly when they're robotic, when they're intelligent. It's worth looking into the slides and recognize there are a lot of different destinations we're sending space robots, from Earth's orbit to the moon, Mars, and small bodies like asteroids, comets. And also in the right-hand side of the table, you can see the different robotic forms. we're trying to achieve, so range from surface rovers, robotic manipulators, sampling tools on the surface of terrestrial, extraterrestrial surface, and also subsurface sampling through drilling. There's also more recently a helicopter that was successfully demonstrated on Mars during the Mars 2020 mission. It is also very interesting to start looking into the future. So one of the landscape that we really look at is the orbital scenario. So this is principally around Earth's orbit. It is believed that in the 2025 and 2035 timeframe, there will be many on-orbit space missions that require advanced AI robotics capabilities. So there are lists of them, range from space debris removal to on-orbit assembly, deployment, servicing of satellite for mission flying, and so on. Although these applications are all around the orbit, but they actually can present very different technical challenges to space robot design, because, for instance, the target object in space might be cooperative or non-cooperative. The platform that deploy the robotic systems from could be pseudo-fixed or could be a free flyer. So for instance, one of the work we've been looking at in the STAR lab is how to autonomously navigate with a spacecraft in orbit to perform orbital servicing and assembly. So this will be target that just we call corporate target. So you have some information of. But due to the limited onboard resources with processing, as well as the harsh conditions in space, that made this kind of relative navigation quite difficult. And we want to develop, more innovative solutions that can rely on less computational power, can work really fast, have a higher accuracy, adaptability. So here we develop a monocular vision-based post-estimation algorithm that can deliver that. It also utilizes CNN-based deep learning to give us that additional ability to adapt to disturbances, unknowns. And our technique has been demonstrated using real-world data set, which you can see from the left-hand side of the film that's playing. That's a video stream from actual mission, where we also tested using our in-house developed virtual realistic simulator that give us more extended data set to test. So that's displayed on the right-hand side of the film, which will play, I think, again shortly. And you can see we're adding extra noise or vibration to make the test more challenging for the algorithm to perform. We're quite pleased that we are ranked top 3 in the ESA Stanford Grand Challenge. But we're also not stopping there. We tested the technique further using the robotic hardware testbed. So as you can see here, in this particular scenario, we're demonstrating the technique where we need to perform a docking to achieve assembly of space mirror segments. So on the left-hand side of the robot, you're saying a docking interface that is approaching the target object, which is in space, carried by another robotic arm on the right-hand side. So you have on the top left corner there, the camera view from the servicing arm. And this is really the interesting bit. You can see actually for that few seconds, the camera view actually lost sight of majority of the target object, but still be able to proceed with the docking quite successfully, and thanks to the machine learning technique. Another example of the importance of visual navigation is looking at manipulation, grasping of a non-covered target. So for instance, this can be used for active space debris removal. So on the film playing on the top, you can see that the servicing arm is sitting on the satellite and trying to go and grasp what we call upper G-kick motor. And this is quite a typical, thing in orbit that can be classified as space debris, or is part of an actual satellite that we typically use as a place to grasp. And because this is a non-covered target, we don't have a predefined docking interface. So you need to use things like a gripper as an end effector to perform that, so-called grasping phase. And this is, of course, post the rendezvous stage. And we tested the solution also using the hardware testbed. Again, the interesting thing here is the solution only rely on very sparse point cloud sensing versus the more dense one, so that we can cut down the computation requirement and make them feasible in real time. And also you can see that the rigidization, which is post-grasping, is also working very well. I think it will play again, as you can see again, how after the grasping, where the gripper autonomously defines the positioning in the grasping points on the curvy surface of the nozzle, where the rigidization is also working quite successfully, as you can see in the last few seconds of the film. Moving on, there's also other planetary scenarios that, beyond the orbit, that space robots are typically asked to go and address. For instance, beyond 2020s, we are seeing a lot of plans or provisions for sample return missions, such as the Chinese lunar sample return, or ESA, NASA joint venture Mars sample return missions. Under these missions, typically we are looking at a sample fetch rover that can explore unstructured terrains and collect surface as well as subsurface samples. Beyond 2030s, you're seeing initiatives to perform manufacturing, assembly, or in-situ resource utilization on the moon. So there is this Moon Village initiative. There's a China-Russians International Lunar Research Station initiative. There are also commercial lunar exploitation initiatives. And around those initiatives, we're seeing a demand of heterogeneous robotic elements, building infrastructure. And we are really looking at developing human and robot ecosystems around the south pole of the moon. So again, just to give you a few examples of the research development we carried out in the Star Lab, one of the things that is extremely important is to look at development of potentially smaller scale surface vehicle, that to enhance the surface mobility, either on the moon or Mars. And here we developed, based on bio-inspired concept, very small rover, only have 4 wheels, and which has active suspension system built on 2 linear motors. So just play the simulation results on the top, 2 videos. So on the left-hand side, you're saying how the small vehicle chassis could perform the crawling behaviors. Well, on the top right, you're seeing the same chassis then can demonstrate the climbing behavior. Of course, we need to actually prove this is working in real implementation hardware system. So on the bottom of the film, you can see, first of all, starting from the left-hand side, how the rover with the active suspension system can basically survive from the entrapment of loose sand terrain. Well, with the exact same system, we also demonstrate the climbing behaviors using the hardware prototype, and that is now playing on the right-hand side on the bottom. So you can probably notice the rock climbing is achieved, I think, at a height of more than 2 times of the radius of the rover well, which is quite impressive for such a small body of vehicle. I think we're talking about, tens of kilograms of rover body here. Just moving on in terms of the locomotion capability, as mentioned previously, subsurface drilling, locomotion is very important. And we know how expensive it can be, particularly in a microgravity environment, using classical methods such as rotary. So here we, really push the boundaries of the knowledge and look into bio-inspired method here and come up with a solution inspired by wood wasp that, look at the penetration in regulars using dual reciprocation motion. So the simulation, that film that is playing right now, demonstrate the traction between the granular particle in the regulus with a drill bit. As you can see, this is achieved by dual reciprocation between the regulus and the drill bit rather than overhead force like the rotary drilling. And this was also tested using hardware testbed that is playing the film adjacent to it. Of course, sampling at multiple depths is very important. For example, with sample return mission. So we incorporated the sampling design into the wasp drill mechanism. And this is also tested using the lab-based test bed. I think the film is also playing on the right-hand side with a color sand, so we can basically mark what depths the sample is collected. Just moving on. This worth mentioning is actually very critical for us to have the knowledge to simulate the extraterrestrial soil and regulus, both physically and digitally. So we have developed facilities in our lab to be able to simulate the planetary soil and regulus that range from Martian soil simulants to icy and non-icy simulants for the moon. Digital simulation using discrete element method is another tool we use because it really provides us very repeatable method, but less expensive compared to hardware testing to look at the robot-soil interaction. So like the film playing right now on the left bottom, and you can see how we could simulate the behavior of the rover on the sand particle. Well, on the right bottom is a similar simulation there to give us very insightful information of the behavior of the drill with different teeth design, with different dimensions, how they behave in the granular particle environment. Looking forward, I think it's fair to say that as a space roboticist, our goal is to really develop AI robotics to enable sustainable space operation. So what that means is in a near midterm, we really need to look at solutions that can perform low computational high accuracy 3D mapping and perception. We need to be energy optimized for the locomotion design. We need to be resource aware for the computational solutions we come up with. We also need to be very sensitive about the parameter tuning. The more we use machine learning, the more we have to be very responsible for our solutions so that the end user don't just have a black box to deal with. Both hardware and software need to be reconfigurable, need to be self-verifiable so that it's a trustworthy system. In the long term, we're really looking at robotics to achieve long-lived operations in orbit with minimalistic interventions. Of course, when you go to the extraterrestrial service, that's probably a very important feature too. Just to give you an example of some of these more future concepts, I think we really need to move from the weak AI to strong AI. One of the attempts we made is to look at reconfigurable autonomy. Where in the example here, we developed solutions for the SLAM that can actually autonomously or automatically switch between different feature detectors so that based on the actual performance of the SLAM for rover navigation, you can basically switch between different feature detection technique to help regain a better solution when your example navigation performance is really decaying. If you're interested in any of the things I talked about so far, there is also a brand new book being launched at the beginning of this year, published by IT. This is a collection of the latest work from actually a team of international authors that cover both orbital and interplanetary missions and how robotics and artificial intelligence is able to help. I think that's all for my slides. I hope it's a reasonable set of information. Certainly welcome any questions colleagues might have. Thank you so much for your time. Thank you.
Thank you so much, Professor Gao, for sharing your impressive work. It's always eye-opening to learn more about the latest technologies for space exploration. And now it's time to take questions. Please feel free to ask if you have any. So, Professor Bao, what do you think is the biggest challenge in operating autonomous systems like robot on or mobile car in the space, because the environment is very different from the Earth? Like, does air density or gravity matter?
Yeah, that's a very good question. So first of all, I would use my previous slides to demonstrate some of the difficulties. So first of all, the visual environment is actually quite different from Earth or the typical Earth environment that we deal with. So for instance, there are extreme lighting conditions. There are a lack of reference point or man-made reference point. So there's homogeneity in space that which made visual perception very, very difficult, very challenging to do. This applies to both the orbital environment as well as the planetary environment. So it is very difficult actually to visually, reliably detect feature and track them and use them for navigation purposes. So this is very hard. Secondly, there are also challenges in terms of verifying and validating your algorithm, because you know most of the VMV is conducted offline, but with a space system, we obviously need things to be quite trusted and robust. That introduce a lot of challenges there. So for instance, we are collaborating with some colleagues in other UK universities to look at verification security aspect of, for example, the navigation for the robotic grasping. And if people are interested, we actually just recently have published paper, just I think this month, on looking at how to perform the runtime verification for autonomous grasping for active debris removal. So if colleagues are interested, you can take a look at the details of that. Yeah.
Okay, thank you, Professor, for your detailed answer.
Thank you, Professor, for your interesting presentation. I had a research advice question. I see from your presentation the space field is still a rich area for developing systems and mechatronic solutions, which is unlike anything on Earth. So such as this car here and the drill system. So if for someone that is not aware of space research, but has interest in this area, where should they start looking into open-ended problems to solve using mechanical, mechatronic, and robotic systems? Reading your book, or is there any specific journal that encourages such research?
Thank you for the question. And I really appreciate that our colleagues, took interest in the space challenges of thinking about, undertaking some of the applications that we're looking at. So certainly, yeah, pick up the book. Hopefully that will give you some examples, because it's very interesting, particularly that IET book I just recently published. In that book, you will find there are contributors that come from robotics lab that are not, traditionally looking at the space problem. But thanks to some collaborative research, they start looking into it. So it's definitely doable for colleagues who work, traditionally in terrestrial problems. So the book is a good place. Another place is actually a journal of field robotics, which I didn't explicitly mention, but in my title slide, I basically give recognition to Journal of Field Robotics, which is widely published journal, which I serve as editor-in-chief at the moment. So it is a journal that really look at publishing robotics work that deals with unstructured environment, very challenging outdoor environment. Of course, space being a key application there, but it's also look at construction, agriculture, mining, nuclear. I think if you think about those environments on Earth, there are some synergies of them with the space applications. For example, with nuclear, we know they have also a similar problem with radiation. With mining, we know they also limited in the communication infrastructure underground, very similar to space. There's also offshore, undersea or underwater, where they have this water pressure. In a way, is very similar to microgravitation field, from the mechanism point of view. So I think probably colleague will be able to find more and more synergies with this other sort of non-space domains and start to realize that there's some, transferability in terms of knowledge and technology across, between the space and non-space applications. Hope that's helpful.
It is very much.
Very happy for you to contact me directly if you want to discuss anything offline.
Thank you for the offer.
Thank you for the presentation. I have just a question about powering the manipulators or the mobile robots in space. So when you try to position them, do you just use solar and is it enough? Do you try to assemble them around the already stationary places where they would charge? Or do you want to actually move them away to explore further?
Sorry, it's a question about power system because your audio sort of broken up a bit while you're talking. So are you talking about the power system? Or,
yeah, and how it affects your decision on where to place the robots in space or where to land? Is it near already built infrastructure, or do you want to go further to explore?
Okay. Thanks for the question. So the existing spacecraft are typically solar powered. So it's a solar power as a primary source of energy. But of course, there are some larger rovers, as you probably came across, that are using nuclear power. So at the moment, there's not yet infrastructure in either Earth's orbit or planetary surface that can provide that powerhouse. So where, is like a power station where robots can go and charge or replace the battery or do things like that. But that is the direction we're heading to. And because of those limitations at the moment, you can appreciate that we have, when we design robotic solutions in terms of navigation and control, we need to be very energy aware because of this limitation on board of the robot. But moving forward, as I was trying to present in my slides as the over the horizon, the future direction, I pointed out, I think in the future, we'll be looking at setting up infrastructures either in orbit or on extraterrestrial services. So this infrastructure would include things that provide, power solutions, energy solutions. And if that is implemented, then it will change the way we design the robots on board, if that makes sense. Yeah.
Okay, thank you, Professor Gao. We are glad to have you to be here. Thank you.
Thank you, everyone, for your time.